Okay, for those watching the video, you didn't miss anything. Okay, so we did density matrices and von Neumann entropy and Renyi entropies, and now we want to talk about when we have multiple systems to get to entanglement. So if we have disjoint systems, just like we did in the classical case, in the quantum case, then they have a joint Hilbert space. So I'll call the joint system AB, which is a tensor product. And so given bases for the two subsystems, we have a basis, joint basis, which is made up of tensor products. So you can choose any basis for A and any basis for B and construct a basis for the joint system, and you end up with the same Hilbert space. So for example, 2 spin halves, we would get all of these 4 states. And we can obviously take arbitrary linear combinations of them. And the point is that when you take some linear combination of these 4 basis states, sometimes you'll get so some pure states in the joint Hilbert space factorize. For example, if I take this particular linear combination, just the sum of them all normalized, this is the product of 2 states in HA and HB respectively. So that one factorizes psi1. On the other hand, if I just change one of the coefficients, so exactly the same, but with a minus here, then you can work out that there is no such decomposition. It's not a product of a state in HA times a state in HB. And so when that happens, the state is called entangled. Otherwise, it's factorized. Okay, so we have these 2 types of states in the joint Hilbert space, and you can imagine that if I give you some, here to convince yourself that this one doesn't factorize, you just play around with some coefficients for a little bit. If I give you some much more complicated Hilbert spaces and some much more complicated state, and then how would you know whether it factorizes or not? That's basically a linear algebra problem, and to which we're going to give one set of solutions. But first, let me back up to sort of make it a little bit more physical and ask the question, okay, so given a state on AB, what does it look like for an observer on A, for example? So if I have a state, which for the moment, so here I was talking about pure states. So when I asked, let me emphasize this. On this board, I had a dichotomy among pure states on HAB between factorized and entangled ones. Now, but what I say on this board, if it fits, is going to be for pure or mixed. What does it look like? I want to ask the question, what does it look like to an A observer? So given an A observable, Well, there's a corresponding observable on AB. So we can define this, just tensor it with the identity on B, and that's the corresponding observable on AB. And if we want now to ask, well, what is the state, given a fixed state rho on HAB, what is the state on A such that, so we get the right expectation values? Whatever. Okay, so one way to think about states and observables in quantum mechanics is that they're elements of dual vector space. So essentially a state is a functional on the space of observables, linear functional on the space of observables. And so what we're asking, so if I know for every OA I have this observable, this corresponding observable on AB, then given rho I know the left-hand side of this, and that fixes actually this state. Okay, because now I have a definite linear map from observables OA to numbers. That's a dual vector, which is a state. So this requirement fixes rho A. Of course, that's a bit of an abstract way to say it. The answer to this question is simply that rho A is a trace on B of rho. Okay, so it's sum on B in any basis. Okay, and you can check that it works, and this is the effective state for observers who are doing their experiments only on A and who don't have access to B. Okay, and so for example, getting back to my two cases, if I calculate, so if I take rho to be psi 1, then rho A, sort of obvious from this expression, just by working in a basis where this is one of the elements for B, I'll, of course, just end up with this, which, of course, is a pure state. I always do this. Somehow, it's very hard to write bras. I always end up writing kets. However, if I instead take psi 2, which is the entangled one, then I get a different rho A. I'm not going to go through the algebra, but what you get is this state. So, in the factorized case, we ended up with rho A being pure, and in the entangled state, we ended up with it being mixed. And it's very easy to convince yourself that this is a general feature, that if your state, if rho factor, if psi, because I'm assuming it's pure, if psi on AB factorizes, then you get a pure state and vice versa. And if it's entangled, then you get a mixed state. Again, in this statement, I'm assuming that the full system is in a pure state. I'm not making any statements yet at this level about when the full system is in a mixed state. Okay? And therefore, since we have a nice way to quantify mixedness, we simply, if we want to know whether a pure state on AB is entangled or not, if we can calculate rho sub A, and if we can calculate its von Neumann entropy, we can determine, in principle straightforwardly, whether A and B are entangled. So, the entropy, so this is the entropy of rho sub A, is a measure of entanglement, and therefore people call it the entanglement entropy. Well, which people? Not people who actually do quantum information theory for a living. They've never heard of entanglement entropy, even though they study entanglement and entropy all the time. Just the phrase doesn't exist for them. It's a phrase invented by people in our field. Okay? And it has its pluses and minuses. I'm not going to defend it, but that is the term people use. And the definition is this. You take the von Neumann entropy of the reduced density matrix. Yeah?
What do quantum information people call this measure of entanglement?
The entropy of A. It's the entropy of A. That's what it is. Because the Renyi entropies are also measures of mixedness, S alpha of A are also measures of entanglement. So if instead of calculating S, you calculate S2, and you find it's non-zero, then you know there's entanglement. If you find it's zero, you know there wasn't entanglement. These are if and only if statements. Okay, so now we have this very bizarre situation that doesn't occur classically, that we know the full state, the precise state as well as we can of the full system, and yet we're mixed, meaning we're ignorant of the state of a subsystem. And the reason this can be possible is because the uncertainty principle guaranteed that in any case, even in the full system, being in a pure state does not mean we have definite values of all observables. And now when we restrict ourselves to A observables, meaning observables of this type, we're talking about a subalgebra of the observables on AB. And so now we have even less information about the state, and it turns out that that state can be mixed. Okay, so really, I mean, there's a very close connection between the phenomenon of entanglement and the uncertainty principle. Without the uncertainty principle, you wouldn't have entanglement in quantum mechanics. Okay? Now, a very useful device from a linear algebra point of view for understanding a pure state is a Schmidt decomposition. Any psi on AB, any pure state, can be written in this way. So where the squares of the coefficients give you a probability distribution, and these guys are orthonormal. orthonormal set. Not necessarily bases. You'll get a basis if, well, actually, let me say that in a second. In this expression, you easily calculate rho A to be, so this set of A's are the same as the eigenvectors of the reduced density matrix. And similarly for rho B. Same equation for rho B. Okay? And so if the reduced density matrix happens to be full rank, then necessarily this is a basis. But it doesn't have to be. Although you can always make it a basis just by making some of the PA 0 if you want. Okay? So this is some linear algebra theorem. Yeah?
Are you assuming A and B are the same order space?
No.
So then why can't I take something like a 2 times L to the R?
Good.
Is A and B?
Good. Oh, good.
Separate sets of bases.
Yeah. Thanks for the question. So this is an orthonormal set of vectors on HA. This is an orthonormal set of vectors on HB. I happen to be using the same label for both sets because they're correlated within this vector in this expansion. Okay? A priori, in terms of the Hilbert spaces, they have nothing to do with each other, but having fixed a psi and expanded it in this way, that induces a correlation. And so I'm using the same label. Okay? Now, what I said about them being bases, of course, falls on its face if they have different dimensions. Okay? Then they can't both be bases. Yeah.
Yeah, can you repeat the argument that entanglement is often different?
Right. So we have a situation where we have a quote-unquote definite state on AB. And yet we have an uncertain state, an unknown state on A. It has some entropy. It's a mixed state. Now, the only way that can be possible is if we didn't know, is if that state on AB did not have definite values of all observables. If it had definite values on all observables, it would have definite values on all of these observables in particular, because this is a subset of the observables, and therefore it would be a definite state on A. Why didn't we have definite values on all observables on AB, even though we had a pure state on AB? The answer is the uncertainty principle tells us that even on pure states, unlike in classical mechanics, even on pure states, you don't have definite values for all observables. So that's the back door by which this mixedness of the subsystem enters into the logic here, which from a classical point of view just doesn't make any sense.
That can have uncertainty principle as well as a pure state of A entropy.
The argument does not say, right, so the argument does not imply that rho A has to be mixed. It just explains how it's possible that rho A could ever be mixed. Yeah. Yeah. You mean when it's, of course, you mean when it's not pure? No. Well, not so simply. So I'm going to talk about that. Yeah. So this implies something useful. So rho B equals the same, in particular with the same PA. So that implies S of A equals S of B. And also S alpha of A equals S alpha of B. So when the full system is in a pure state, the two parts both have the same entropy and the same Rennies for all alpha. Okay, so we got entropy out of entanglement. And now we're going to go the other way. Given an arbitrary rho A on HA, so on this board, I'm not assuming that rho A comes from any particular rho AB or any particular psi AB. I just told you rho A. I didn't tell you anything about what's going on B. Okay? I can construct a pure state on AB whose reduced density matrix is rho A. Okay? Can construct a Hilbert space HB and a pure state psi AB such that rho AB equals trace on B psi AB. And this is called a purification. So I start with a mixed state and I embed it in a larger system such that it becomes pure. And how do I do this? So just write, first what you do is you diagonalize rho A. It's a Hermitian operator, so that's not a problem. Then you choose, you just construct yourself a Hilbert space whose dimension is at least the rank of rho. For example, I mean, there's quite a bit of freedom in this construction. For example, you could just choose HB to be another copy of HA. That would be the simplest thing to do. But you don't need it to be that big, necessarily. And then you choose yourself some orthonormal vectors within HB. And you just go the other way from the Schmidt decomposition.
Should that be rho A after such that it is like tracing over B, right? The left hand side.
Thank you. Yes, thank you. And then you define the purified thing. Basically, like I said, just go backwards from the Schmidt decomposition. Okay, so given an entangled pure state, we get entropy. Given a mixed state, we get an entangled pure state. So if, by the way, if rho A had happened to be pure to begin with, then this decomposition here would have a single PA which is non-zero, which is 1. And then this would have a single term in it, and this would be factorized. So if this is pure, this is factorized, and vice versa. Okay? So what's the lesson? The lesson is that, I know I'm not supposed to write down here, but let me just, it's just a very simple thing, just 2 words. Entropy and entanglement are interchangeable. And so in some sense, if you want, you can think of all entropy as coming from entanglement. Anytime you have a system with entropy, you can just imagine that it's part of a larger system that's in a pure state. And that's actually a very handy technical tool in quantum information theory, is to always have hanging around a purifying auxiliary system. Yeah?
What about the system with some large gravity?
Well, you can choose, so if the state you're talking about is, let's say, a uniform mixture over all the ground states that has entropy, so that would be the 0 temperature thermal state, you can imagine that there's some auxiliary system that basically is entangled with it, which keeps track of which one you're in. So I'm actually going to do a thermal system next, And then you can take the 0 temperature limit of that if you want. Okay? So I'm going to do the purification of the Gibbs state. This is a very important example. So rho A is 1 over z e to the minus beta. And then, or if you want, and now these are the eigenstates, e to the minus beta EA. These are the energy eigenstates. Okay, so the purification looks like this. And let me just choose HB to be another copy of HA, okay, the Hilbert space. So these are energy eigenstates of HB, where my Hilbert space is a copy of my original one. And this is an important enough state that it gets a name, although the name is pretty obscure. It comes from somewhere, I'm sure. Thermo field double. Well, double is fine. I've just doubled my system. And by the way, notice that this is a pure state on my doubled system, which happens to be an energy eigenstate. Well, let me not say energy. It's an eigenstate of the operator HA minus HB. Because it's a superposition of states that have the same A and B energy. Okay? I mean, it's not the only such eigenstate, but it is an eigenstate like that. And this will be useful later on. If your Gibbs state, if you want to think of it as being prepared by a path integral, like if you're doing quantum mechanics and you do a Euclidean path integral, you can use that to prepare your Gibbs state by considering the path integral on basically a finite Euclidean time interval beta. Then I can prepare this state on my doubled system by a semicircle. So let me first write this operator is prepared by the Euclidean path integral on an interval of length beta. So this is where I stick my ket. This is where I stick my bra to get the matrix element of this operator. And then this guy, the Thermo field double, is prepared by the Euclidean path integral, well, Euclidean path integral on a semicircle of length beta over 2, circumference, whatever, beta over 2, where this is my A system and this is my B system. So if you want to know the overlap between psi AB and some given AB state, you put the A state here and the B state here, you calculate your path integral with those boundary conditions, and that tells you the overlap. It's very handy to have path integral representations of all of these gadgets, especially when we get to field theory. And let me say one other thing as a teaser for holography. The Thermo field double So a thermal state in holography at sufficiently high temperature is represented by a black hole. The thermofield double state is represented by, again, a solution to the Einstein equation that has two boundaries, one for A and one for B. And that solution to the Einstein equation is the double-sided maximally extended black hole. I'm going to come back to this. Whoops. Maximally extended black hole, whose Penrose diagram looks like this. This is our original system A, and this is the copy B. Now, this way of writing rho sub A kind of gives us, or yeah, so we're, as physicists, we're kind of comfortable with Gibbs states. And so it sometimes makes us feel better to pretend like an arbitrary rho sub A is a Gibbs state. And luckily we can do that. So any state, pure or mixed, can be written in this way. And I'm going to leave off the beta for some HA, for some operator. And HA is actually only defined, so you can take HA just to be minus the log of rho sub A, and then Z is 1. But sometimes it's convenient, as we'll see, to choose HA to be something else such that Z, the normalizing factor, is not 1. Okay? So this is just for convenience. We give ourselves this freedom to shift H in some useful way, and then we get some non-trivial Z. And HA, so which is defined up to constant, up to an additive constant, is called the modular Hamiltonian. This term modular arises from algebraic quantum field theory, where this plays an important role. Now, if we manage to do that, if we manage to know what this is somehow, if we're clever enough, then the entropy is just the expectation value of HA plus log Z. So this is the usual, like, this formula from high school. Free energy is E minus TS. This is like that. This is F. And the T is, I've set the T to be 1. And so if we can figure out what this is in some useful way, such that we can compute its expectation value, and we can compute this, then we're good to go. So this is sometimes handy. It should be said that this expectation value can actually be evaluated in the full system. So not necessarily in just the A system, but in the full system. Because I can regard HA as being an operator on the full system. It's born as an operator on A, but I can regard it as an operator on the full system, and that doesn't change the expectation value. Now, the problem is that it's pretty rare for us to know HA in any useful form.
So the modular Hamiltonian can take different values depending on what are C, right?
It'll shift by a constant, or let me put it Z is a number, by the way. Sorry, Z is a number. This is an operator. This is a number. This is just, yeah.
So for different choices of Z, does HA change?
Or let me put it this way. If I shift HA by a constant, Z changes. I'm just defining Z to be whatever it has to be such that this has trace 1. Z by definition is trace e to the minus HA. So if I shift HA by adding a constant, then Z gets multiplied by e to the minus that constant. Okay, this is just a normalizing factor. Okay, so far I've mostly been assuming that my full system is pure. But what if it isn't? I'm going to run out. This is the last, at this rate. Yeah, there's no chalk in here. I'm going to need new chalk in about half an hour. Is that the secret stash? Okay, now the problem with the term entanglement entropy, yes?
Sorry to come back to it, but I still
Yeah.
have a question about this 1 over Z minus beta and H as an operator, and
So let's say you want to compute a matrix element of this between two states. Yeah, so you can calculate that matrix element in the following way. You attach the state as a boundary condition. Let's say, for example, it's a position eigenstate. You make a boundary condition on your path integral that the position on this has to be whatever it is in the ket, and on this it has to be whatever it is in the bra. And then you compute your path integral with those boundary conditions, and that tells you the matrix element. Yeah, actually that tells you the matrix element of this, and then you have to figure out what 1 over Z is, to be more honest. Well, yeah, so the term Hartle-Hawking state refers to the state of the fields on this, and indeed you want to put the quantum fields on this in the Hartle-Hawking state. To be a little more, I was just talking on the classical level. Any other questions? All right, proceed. Well, let's say let's not assume anymore that row AB is pure. So I have some row AB, and I compute row A, and I compute S of A. And let's say I find it's non-zero. Does that mean I have entanglement? Well, let me give a counterexample. Let's say row AB is just row A times row B. That's consistent with this notation because once I trace over B, I'll get back to row A. And let's say row A happens to be mixed. Would you say that this is an entangled state between A and B? Not really. It's not even not entangled. It's not even correlated. So that means that SA being positive does not imply entanglement or even correlation. And that's why the term entanglement entropy, which is applied to this, is a terrible term. And now what I want to do is just define what I mean by correlated. So
The statement is that A and AB are similarly entangled with something else that you've already traced.
well, you are free to purify this. You're free to purify this, and in fact, you can do it in such a way that A and B are separately purified. A gets its A prime, and B gets its B prime. But are A and B entangled? I would say no. I don't know what, okay. I've come to the end of my algorithm for board work. What do I mean by correlated in this context? I only defined entangled for pure states. Let me define classically correlated. Rho AB is classically correlated also called separable if it can be written in this way, as a convex combination of product states. Where this is a probability distribution. So you would agree, I think, that anything of this form is uncorrelated. And now if I allow myself just convex combinations, and that's what kind of makes it classical, so I'm not taking superpositions now, I'm just mixing. I have various uncorrelated states which I'm mixing, not superposing, and I get some state. If I got that state just by mixing uncorrelated states, then the only kind of correlation I introduced was of a classical nature, and so that's considered classically correlated. Otherwise, you say it's entangled. Okay. And one characterization, one operational characterization, is that these states can be prepared from uncorrelated states by operations that are called local operations in classical communication. Meaning if Alice and Bob want to prepare a joint state on their joint system in separate labs, they can make any state of this kind by doing separate operations on their own systems and talking on the phone to describe what to do next and to make measurements so they can make separate measurements. Thanks. And they can agree on what to do as long as all communication is classical. So they're not sending qubits to each other. They're sending bits. That's fine. But they're not sending qubits. And then they can make any state of this form. So separable states can be prepared, so here's a bit of jargon, by LOCC, which means local operations and classical communication. So people who do quantum information theory are extremely interested in separable states as a class of states because somehow these are easy. You know, sending qubits is a bit dicey in the mail. You never know what's going to happen to them along the way, but sending bits we pretty much know how to do. And then doing just local operations is fine. So if you want to talk about some quantum cryptography or something like that, then it's very important to know which kinds of states you can do this way and which kinds of states you can't. In other words, you actually have to find a way to physically send a qubit from one place to another. Yeah?
So what is convex?
Convex means a linear combination. All of the coefficients are positive and they add up to 1. That's a convex combination. Yep. Now, before we had this awesome characterization of entangled states, which is those that have positive entanglement entropy. We've already seen that that's a terrible criterion on mixed states, fails completely. So what can we do to know whether rho AB is entangled or separable? Well, we already saw that for probability distributions, and probability distributions, joint probability distributions are a special class within the separable states. For those, we had this, recall. Okay. And you can show that this is true in general for separable states. A little bit of linear algebra. So if you compute these and you find that this fails, then you know that rho AB is not separable. It's entangled. So, so the conditional entropy defined as before is a diagnostic of entanglement, meaning, by which I mean that if you calculate and you get a negative number, then there's entanglement. So let me write. Being negative is a diagnostic of entanglement. But the other way around does not hold. It's not true that every entangled state has a negative conditional entropy. And in general, actually, it's very hard to know whether a given state is entangled or separable. In fact, it's proven that it's NP hard. So there's no algorithm, sort of efficient algorithm, for distinguishing between entangled and separable states. And there's nothing like just calculating some von Neumann entropies and this fact, so entangled mixed states, is NP hard. So this fact has given rise to this problem of distinguishing has given rise to a large part of quantum information theory is devoted to ways you can tell whether a given state is entangled or separable, a given mixed state. And there's no one way to do it. There's many different ways to do it that are sort of measuring. So what this says actually is that the notion, there's no sort of clean theory around this question. Okay? And you could also ask the question, just like in some sense, the von Neumann entropy, if rho AB is pure, the von Neumann entropy of rho sub A measures how much entanglement there is. And here you could ask, well, given a mixed rho AB, how much entanglement is there? And there's not one canonical answer to that question. There's many different ways to answer that question, to get numbers which answer that question and satisfy different properties. And most of them you cannot calculate anyway. So an example of one that you can calculate would be this, or minus this. Another one you can calculate in some cases is called the logarithmic negativity. So a calculable diagnostic, or another, I should say another, is called the logarithmic negativity. And I mention it because, as opposed to all the others that I'm not mentioning, and yeah, this one is not even particularly famous for people who do quantum information theory. They prefer others. But it's famous for people who do field theory because we can actually calculate this in field theories. That's why I bring it up. So it's been calculated in field theory. None of the others, as far as I know, has ever been come close to being calculated in field theory. Yeah. So the problem is I give you a row AB, and you tell me if it's separable or entangled. And my n is the log of the dimension of the Hilbert space in the asymptotic analysis. Oh, I think if it's separable, I have to tell you, I have to write it in this form. So, yeah. So in the notes that I'll post, I actually describe logarithmic negativity, but I'm going to skip that here. Okay. I want to make some quick comments. I hope they're quick. On the physical importance of entanglement. So entanglement, decoherence. This is going to be pretty sketchy. And monogamy. Okay, so the first statement is that entanglement is ubiquitous. And the reason it's ubiquitous is that any sort of interaction so interactions between two systems tend to lead to getting an entangled state. And one implication of this is that interactions with the environment decohere your system. So for example, so if there's some environmental degree of freedom that your system is interacting with, they'll tend to get entangled. So if you have some system of spins, say spin up and spin down, and it interacts with the environment in such a way that if your system is in spin up, so this is your system, and this one is the environment, tends to leave the environmental variable the way it is, but if your system is spin down, and let's say the environment comes to you in the state 0, so notice that your system is not affected here. But it's having an effect on the environmental degree of freedom, which is flipping it. And then now you've carefully prepared, you've done a lot of work to prepare some particular superposition on your, on your system. Then by the linear time evolution of quantum mechanics, now you have yourself an entangled state. So you've become entangled with the environment, and now the environment is some photon that just bounced off your system and went away. You have no idea what it's doing, where it is. And so the only thing you're left with is rho sub A. So rho sub A started in this state, which in the up-down basis is this. And now it became this mixed state. So this is a pure state. And now your off-diagonal elements have been zeroed out. And you now have a mixed state. And so whatever experiment you were planning to do with this careful superposition that you prepared is not going to work, because now you just have a mixture of up and down. Okay? And this is actually why, so in general what happens is that for any system, interactions with the environment decohere, where decoherence here means that in some basis, which depends on the details of the interactions with the environment, the off-diagonal elements of the density matrix, of the reduced density matrix, decrease in magnitude. And you can show that if you fix the diagonal matrix elements and you decrease the magnitude of the off-diagonal elements, the entropy increases. Okay, so this is basically the short reason why it's so hard to build a quantum computer. So in a classical computer, you have some bits for your memory, and of course you want to protect them from being disturbed by the environment. And the way you do that is by making them at least a little bit macroscopic, so that they're kind of stable against small perturbations from the environment. But in a quantum computer, that's not nearly enough. You need to protect the environment from perturbations from your bits of memory, because otherwise your bits of memory will be decohered by the environment. So you have to actually protect the environment from your system, which is much harder than protecting your system from the environment, because now if you say, okay, I'll just make my bits macroscopic, the more you do that, the more decoherence you get. Okay, so you have to keep them microscopic, you have to keep them basically some kind of elementary degrees of freedom, and now you've got the problem of manipulating elementary degrees of freedom. Okay? Okay, I want to emphasize one other thing that's sometimes forgotten in discussions of reduced density matrices and entanglement entropies, which is that what you get for an entanglement entropy depends on how you know, so far this was some math, which is perfectly unimpeachable, but then in the physical application, you have to ask yourself whether you're using the right mathematical tool. And so I want to emphasize that you have a choice given some system of how you do the decomposition. And you'll get a totally different answer depending on how you do it. Okay? So let me give a really stupid example. So I have a hydrogen atom, so a proton and an electron, and so I have my position of the proton, and I'm going to work, so so the center of mass position is basically the proton position, and then I have the electron position. Okay, and let's just work in the Born-Oppenheimer approximation, where the wave function for the full system is given by some wave function for the center of mass times, I'm going to assume the hydrogen atom is in its ground state, so we're working that sector of the Hilbert space, times the hydrogen atom ground state, the one in the textbooks, of the relative position. Well, this is obviously entangled. So if I give you, if the hydrogen atom is somewhere in some box, it has some wave function in the box is much larger than a hydrogen atom, then you get entanglement, and if you calculate rho for the proton, you get a very mixed state. So you would conclude that the proton is in a very mixed state if you, let's say, don't know where the electron is. Okay? Or you could say, oh, I'm going to use a different coordinate system. I'm going to define my relative position to be this. And then guess what? Factorizes. And now I calculate rho sub r. I'm calculating rho for the same degree of freedom. And I get a completely different answer. Pure state. Now, both are mathematically correct, okay? They're just answering different questions. And in particular, I think it's probably more common that one would be interested in the type of question where you get this answer, and the physical reason is that the electron doesn't decohere the proton. So you can do a double slit experiment which relies on having an undecohered, I should just say coherent state of the proton on a hydrogen atom, no problem. And the reason is that the electron state is slave to the proton position. It's not independent. And so tracing over it, while it's mathematically correct, doesn't really answer a very physically relevant question. And another way to say it is that, I think it's here somewhere. Nope. It went away. Another way to say it is that given an operator on the proton Hilbert space, you want to promote it to an operator on the full Hilbert space And the way that I did that before by tensoring with the identity is just the wrong way to do it. And in general, that's true if you have a slave degree of freedom. Okay, so you can actually write an operator on the full system, which is the appropriate position operator for the hydrogen atom. Okay, and it's basically what would be that times the identity on the identity acting on the relative position. And so in an example like this, rho sub A isn't really the correct representation of the effective state for H sub A. And this, so I want to bring this up because in the context of field theory, it leads to the following confusion that you often hear. In an interacting field theory, you have your UV modes and your IR modes, and by virtue of the interaction, they're entangled with each other, even let's say in the vacuum, so in the ground state. If it's a free theory, every mode is in its own ground state and they're not entangled, just a tensor product over all the modes. But in an interacting theory, that's not true. You have entanglement between the UV and IR modes. And people sometimes say, therefore, the IR is in a mixed state. And mathematically, you can define a reduced density matrix for the IR modes, and you will get an entropy. But the entropy you get depends very much on your choice of variables. And in any case, so if you make some change of variables like this, you can change the value of the entropy for these IR modes. And the reason for that is that the UV modes are actually slave to the IR modes. Let's say in a Wilsonian picture, where basically for any given value of the IR modes, the UV modes are in their ground state for that value of the IR modes. Okay? Similar to a Born-Oppenheimer approximation. And because they're slave to the IR modes, they don't decohere the IR modes. Okay? So the fact that a proton is actually made of quarks, so it has these internal degrees of freedom, those internal degrees of freedom, as long as you're not at high enough energies to excite them, they don't decohere the proton. You can do whatever experiments with the proton spin and position and just forget about the quark modes. You might think, because I can't see the quarks, I should trace them out and get a mixed state. But it's a difference here between tracing out, and this is another pet peeve of mine, tracing out and integrating out. So integrating out a degree of freedom, let's say some very massive or fast degree. Normally you have some separation into fast and slow degrees of freedom, and you integrate out the fast ones to get an effective Hamiltonian for the slow ones. That means that you fix the state of the fast one in terms of the state of the slow one, and that means it doesn't decohere the slow one. Versus if you traced over, you would do that. So don't mix up integrating out, which is something we do in physics, which is very, very important, and we do it to internal or fast degrees of freedom with tracing over, which is something that's more useful when applied to external or environmental degrees of freedom. These are very different things, okay? Okay, that was my little sermon on the topic. See, the purpose of giving Tassi lectures is to vent on things that you hear people say. Okay. Now, I said that entanglement is ubiquitous because interactions lead to entanglement. I also said that entanglement leads to decoherence, and decoherence destroys entanglement. So, entanglement leads to decoherence, which destroys entanglement. Okay? So if I have, so as an example, if I start with this nice entangled state, and I decohere it in some basis, I'll get this state. Okay? So that means that, so the fact that entanglement creates decoherence and decoherence destroys entanglement means that there's an incompatibility between entanglement within a system and entanglement with other degrees of freedom. They exclude each other. Okay? Yeah. No, well, this is sort of in a Wilsonian point of view where we divide our modes into, short wavelength modes and long wavelength modes, right? And I'm taking, okay? And then if we're going to describe, let's say, the ground state of the theory mode by mode, what we would do is, for any state of the long wavelength modes, in that state, we would put the shorter wavelength modes, which are considered fast degrees of freedom, into their ground state. Their ground state depends on the values of the long wavelength modes. And then you can sort of keep doing that mode by mode. This is, okay, so there's an additional confusion which I don't want to, or not confusion, but issue which I don't want to go into, which is we normally learn about Wilsonian RG in sort of a Euclidean context. And there, so you're in Euclidean momentum space and so on, whereas the language I was just using just now was a language of sort of a Lorentzian picture or a Hamiltonian picture. That, yeah. Yeah.
Sorry, maybe I missed it, but what changed from left to right?
Oh, you can't see the subtle difference in You have to look much more closely.
Oh, now I see it. Yeah.
Okay. Okay, so this means that entanglement within a system excludes entanglement with other degrees of freedom, and vice versa. So, for example, consider this state, which is just the purification of this one, the GHZ state on three parties. Okay, so here's A, B, and C, and let me now ask the question: are A and B entangled? So at first sight, you might say, well, clearly they're entangled because here I have a superposition of states. In the first state, A and B are both up, and in the second state, A and B are both down. So they're correlated within the superposition, so clearly A and B are entangled. And it's a superposition, it's not a mixture. You would be wrong, because if I ask a question about A and B, you have to answer it by looking at not row ABC, but row AB. And what is row AB? Row AB is this. Because once I trace out C, I've decohered the superposition, and I'm left with a mixed state, and this mixed state is unentangled. It's separable. So in this state, A and B, despite appearances, are not entangled. Although A is entangled with the BC system, and AB is entangled with C. But A is not entangled with B. So you have to be very careful about exactly which subsystem you're looking at when you ask the question of whether two parts are entangled or not. And in general, you can show Well, in various ways, and I'm not going to explain this, and this depends on the measures you're using, but the more entangled A and B, the less AB is entangled with C. For example, if AB are in a pure state together, and then you purify them, you can purify it trivially just by adding any C you want in a totally uncorrelated joint state, and it'll be totally unentangled with C. So in that limit, if A and B are maximally entangled, then they're totally unentangled with C. And this fact, which is not true of classical correlation, is called monogamy of entanglement. And it's incredibly important in quantum information theory. It's basically, I mean, quantum cryptography is based on this. I mean, in some sense, quantum cryptography is based on the fact that if somebody manages to get entangled with some AB system, Alice and Bob are trying to communicate using some entangled state. If there's an eavesdropper, they can detect that there's an eavesdropper because the eavesdropper necessarily destroys the entanglement between Alice and Bob. Also, monogamy comes up in the firewall argument, for example, about black holes. Okay. Any questions before I go on? Okay, so, I'm looking at the clock. Everyone's turning around. What is he looking at? Okay. Let me just say a few more things, then I'll let everybody go. Okay. About the mutual information, so just as for classical probability distributions, you can show that the von Neumann entropy is extensive, which means that if rho AB is rho A times rho B, then S of AB is just the sum. And in fact, the other way around is true, and otherwise it's non-negative. Otherwise it's positive. So otherwise, this is a less than. Okay. So if we define the mutual information in the same way we did classically, then this thing measures correlation, quantifies correlations. This property, this fact, is called subadditivity. Now, by correlations, here I mean both entanglement and classical correlation. So let me give an example. If I have an entangled, maximally entangled state of 2 qubits, like the lovely one before they sadly got decohered here, and I compute S of AB, that's 0. S of A, on the other hand, is log 2. S of B is log 2. And so I get 2 log 2. So for example, maximally entangled qubits give a mutual information of 2 log 2, whereas if they're just classically correlated, as they are here, then S of AB is log 2, S of A is still log 2, S of B is still log 2, and so I just get log 2. So perfectly correlated bits give log 2. And in fact, the fact that this is twice this, you can see in various protocols, like in superdense coding, which is a trick, like a party trick for coding information in half as many qubits as you thought you would need, and it's that factor of 2 is can be found in here. Now that said, it kind of, in general, I mean, these are simple examples where here it's clearly entangled, here it's clearly classically correlated. As I've emphasized, in general, we can't really separate. There's no single canonical way to separate these things. So if you just calculate a mutual information, you discover whether there's some entanglement and or correlation. It just gloms them together. Okay? And let me just say one last thing about the mutual information. It tells you about correlation, so you might think it's related to correlation functions, and it is. So we have this bound on correlators. So given operators O, A, and OB, the conventional way to know whether they're correlated is by calculating the correlator. And this thing, I'm in a state of bound, which bounds it by the mutual information. But I need to normalize these because the left-hand side, you could multiply OA and OB by 7, and you would make this as big as you want by multiplying it by larger and larger factors. So there's a normalization factor. And unfortunately, the normalization factor is the operator norm. I'll say why I said unfortunately in a second. You square this baby, and this is your bound. And so it tells you, it gives you a quantitative relation between how big correlators can be and your mutual information. And the point here is that the left-hand side depends on an astute choice, if you want to know whether there's correlations, on an astute choice of OA and OB. If you got 0 here, that doesn't mean there's no correlation. It could just mean that the correlation is hidden to you. You don't know the right variables. But if you can calculate this and you get something non-zero, you know there's correlation. If you get something 0, you know there's no correlation. End of story. Okay? So this detects even hidden correlation. Now, one thing that's kind of sad about this bound for our purposes as field theorists is that these operator norms basically are always infinity for any operator we care about, so the norm is actually kind of useless. So I will break it off there, and I promise next time we will get to field theories. Yeah.
This bound is always a little mysterious. Is the proof of it kind of complicated, or is it kind of straightforward?
That depends on how much knowledge of the tricks of the trade of quantum information you come to it with. For quantum information, people consider it like completely obvious, to the point where they don't even know or cite the first paper where it was written. But if you don't have the tools, then it takes a few steps. I mean, one thing to say is that the left-hand side, by its definition, is always less than 1. So this really only comes into play when the mutual information is very small. It tells you almost nothing. If you have like a huge mutual information, there's no way you'll saturate this. But it's not that hard. I mean, I can give you the paper and you'll be able to read it. It's not that big a deal.
One more question.
Or 0 questions. Oh.
So yeah, could you explain again what in the case of this when consider about state, then the higher energy states are written to be ground state. But if we consider about, for example, scattering, like low energy scattering, but I have chance to set those higher energy states, right? So those are two different things. Right?
Yeah, so if you do, so I mean, a scattering experiment, you can certainly detect whether your system is coherent or not, whether you've, so if your particles that you're scattering are interacting with the environment enough to decohere their state, it'll affect the result. If they're scattering at low enough energy that their internal degrees of freedom are not excited, that will not decohere the state. I mean, in some sense, phenomena like deep inelastic scattering can be understood as a decoherence that happens when you have enough energy to actually go ahead and excite the internal degrees of freedom, meaning you kind of see the constituent nature of the protons that you're, of the proton that you're probing with an electron, for example. The electron has enough energy that it's actually seeing the quarks inside. And so there you do an incoherent sum over the possible outcomes in terms of the electron, because the electron has excited the quarks in various possible different ways, and so you have to do an incoherent sum. So that's an example where now you do have decoherence happening from internal degrees of freedom because you have enough energy in your experiment to actually excite them. But to the extent that those degrees of freedom remain internal, they don't decohere the experimental degrees of freedom.
Well, we are looking at rows. Are you like the deep them, or you do the decoherence?
No, I would say if in a Wilsonian RG flow, the UV modes do not lead to a mixed. You shouldn't think of the long wavelength modes as being in a mixed state due to the fact that they're entangled with the UV modes if you're just doing some kind of Wilsonian picture. You don't gather entanglement. You don't gather entanglement as you do a Wilsonian RG flow. I shouldn't have said that. You don't gather entropy. That's what I meant to say. You don't gather entropy as you do a Wilsonian RG flow.
So you don't think that the A theorem or the C theorem has anything to do with entropy?
So in the A theorem and the C theorem, the kind of entropy, the entanglement entropies you're talking about, and this is important, are not between different modes. They're between different spatial points. So you're talking about a spatial entanglement entropy. You're doing a decomposition not by momentum modes, but by spatial regions. And it is true that if you look at a spatial region, even in the ground state, the exterior effectively decoheres the interior, and vice versa. And so you have a mixed state, and you you have an entropy, which is a physical quantity. One way to say that is that the thing is invariant, basically. Doesn't depend on some arbitrary choices you make. So in fact, this kind of spatial decomposition is what the rest of my lectures are going to be on. Yeah. Yeah. Oh, well, it's different from doing spatial entanglement entropy. Spin blocking is a kind of a momentum mode thing. In fact, I'm going to kind of give an example of that in the next lecture. Well, maybe, okay, I'll tell you what, because I think we want to wrap it up, but maybe at the beginning of the next lecture, when I give a simple spin blocking example, we can try to clarify what I mean about when you get decoherence and when you don't get decoherence. I mean, it's a very good, yeah, it's a good question.